I'm going to show you how to find extreme values of functions. If you haven't watched the previous video on the extreme value theorem, I highly recommend you go back and do that first. By the end of this video, hopefully you'll understand how to find extreme values, meaning maximums and minimums of a function, and where they occur, graphically and analytically. We're going to prove those extreme values using calculus methods. And we're going to find critical values and critical points of functions. I'm going to go ahead and assume that's some new vocabulary. A critical value, and this is just vocabulary, is one that makes a derivative equal to 0 or undefined. I'll tell you what, you want to always say or undefined. If I've seen anything over and over again, a lot of people by the end of the year forget to set their derivative equal to 0 when looking for critical values. Let's see an example of that. So let's say you had y equals 1 over x. Well, that's not a derivative, so y prime, think of 1 over x as x to the negative first power. So you can use the power rule. So let's set that thing equal to 0, and you get negative 1 equals 0. Oh, I guess 1 over x has no horizontal tangents, since that derivative is never equal to 0. Oh yeah, that's totally true. But negative 1 over x squared is undefined at x equals 0. That's a critical value. And that's not shocking that 1 over x has a derivative undefined at 0, since 1 over x is undefined at 0, and it's darn impossible to find the slope of a tangent to a curve where that curve doesn't exist. Okay, so let's find critical values for x squared minus 3x plus 2. Are you imagining what that graph looks like? So you should be imagining, we'll ignore the axes, just some parabola. How many critical values is that graph going to have? Just one. Where that derivative is equal to 0. Okay. So if we're going to find critical values, the first thing we do is find a derivative. So we're going to say let y prime equal 0, and then we're also going to say, so we don't forget about the undefined thing, y prime is never undefined. How do we know that? Well, because 2x minus 3 is a line, and lines have a domain of all real numbers, continuous everywhere, all that good stuff. So 0 equals 2x minus 3, and x equals 3 over 2 is the only critical value of y equals x squared minus 3x plus 2. Pretty easy. That's the first step, is finding critical values. What about x to the 2/3 power? Do you know what x to the 2/3 power looks like? Well, let's think of some points we know. Yikes! So some points we know that are on x to the 2/3 power. 0 to the 2/3 power is 0. 1 to the 2/3 power is 1. Negative 1, wait, can we raise negative 1 to the 2/3 power? Yes, because this 3 is the cube root and this 2 is a squaring. We can take the cube root of negative numbers and we can square negative numbers, okay. That doesn't seem right. Maybe we need another point. What number can we take the cube root of aside from 1? 8. So over here, at 8, the cube root of 8 is 2, and 2 to the 2nd power is 4. X to the 2/3 power looks about like this. So how many critical values is this graph going to have? Where is its derivative equal to 0 or undefined? Well, it doesn't appear x to the 2/3 power has any places where its derivative is equal to 0, and has one place where its derivative is undefined. Over here it's 0. So let's see. Y prime is 2/3 x to the power negative 1/3. Let's rewrite that. Y prime is 2 over 3 times the cube root of x. So let's let y prime equals 0. And 0 equals 2. Okay, that's not true, which means y equals x to the 2/3 power has no horizontal tangents, since the derivative of y is never equal to 0. Okay, let y prime be undefined. What's that going to mean? That's going to mean 0 is equal to the denominator. And you can probably do that in your head. That's going to be when x equals 0. So x to the 2/3 power has critical values, or a critical value, only at x equals 0. So if you're given a question in an AP Calculus class about finding global extreme values, you might hear the word absolute as well. And hopefully that makes sense. Anywhere on the globe, the highest, the absolute, the biggest, the smallest, that should make sense. So the first thing we want to do is determine continuity, because if you're given a function that's not continuous, it may not have a maximum and it may not have a minimum. Then you're going to find the first derivative of that function so that you can find the critical values. And then you're going to evaluate your function at the endpoints and critical points. And that's it. That's how you find absolute maximums, absolute minimums in AP Calculus. Let's give you an example. So y equals x squared minus 4x plus 3. Hopefully that factor is pretty easy for you. Oh, wrong place for your axis. This is going to look like this. Now, because you know we're talking about a parabola opening upwards, this thing is not going to have an absolute maximum. It's not going to have a global maximum. It just has a global minimum. And so this really isn't an AP question, but we want to start with easy things that you already know. So after we think about the graph we're given, let's find y prime. I'm going to use the original x squared minus 4x plus 3, so I don't need a product rule. The derivative of x squared is 2x, and the derivative of negative 4x is negative 4. The derivative of the constant 3 is 0. So we're going to say let y prime equals 0, and by the way, y prime is always defined. I'm writing that so you remember to think about a derivative equal to 0 and a derivative undefined. So let's see, what do we do next? Oh, we're in the middle of that, finding critical values. So 0 equals 2x minus 4, and x is equal to 2. So that means, kind of with everything else we know, that this local minimum must occur at x equals 2. So we're supposed to evaluate our function at endpoints and critical points. I guess we can only evaluate at the one critical point. So using x equals 2, y is equal to 2 squared minus 4 times 2 plus 3. Y is equal to negative 1. So we don't quite have an answer. Y equals negative 1 is the global minimum of x squared minus 4x plus 3. Should we find the x value? We already did. Do we need to include that in our answer? No, because it said find all global extrema, or find all the maximums and the minimums. So in this case, we just want a y value. Okay, here we go. Even better. Now this is going to be possible. X squared minus 4x plus 3 is a polynomial, and all polynomials are continuous. So we're given y equals x squared minus 4x plus 3 is continuous on the closed interval -2 to 5. So both maximum and minimum are guaranteed. Okay. So this is going to work out much better than our last example. We already know those x-intercepts, and we're going from 5 to -2. Ooh, bad graph. And so hopefully we'll be able to find the maximum and the minimum. So first we're going to find the derivative of y, 2x minus 4. Let y prime equal 0. Y prime is never undefined. Maybe always defined. And 0 equals 2x minus 4. X is equal to 2. Okay. Are you confused? We were supposed to find a maximum and a minimum, but we only found one critical value, x equals 2. Well, that's okay. We're just going to evaluate x squared minus 4x plus 3 at -2, at 5, and at 2. We evaluate at the endpoints and all the critical values. So y equals, maybe I should say using, x equals 2. So that's going to be 2 squared minus 4 times 2 plus 3, which is -1. Using x equals -2 is going to be, so 4 plus 8 is 12, plus 3 is 15. So far, that's definitely a maximum compared to -1. And then using x equals 5. So that's going to be 5 squared minus 4 times 5. So 25 minus 20 is 5, plus 3 is 8. So which one of these is the maximum? It's pretty easy. You just choose the largest, 15. Which one of these is the minimum? Pretty easy. Choose the smallest. Why did we only need to look at the endpoints and the critical values? Well, look at the graph. Could you find a maximum kind of right here in the middle? No, because it's not a critical value and it's not an endpoint. Okay, I wish I had more room. Unfortunately, I'm going to have to erase. And I'm going to erase this work here because I want to refer to those last things I wrote. So please imagine I'm writing at the bottom of my page, not above. I didn't plan this well. So let's see. The global maximum of x squared minus 4x plus 3 is 15, which occurs at, where did it occur? X equals -2. Okay. What am I going to write for my next sentence about the global minimum? The global minimum, the lowest y value of x squared minus 4x plus 3 is -1, which occurs at x equals 2. Okay, so what do we do first if we're going to find all global extreme values for x cubed minus 3? Well, we kind of quit. We could do the work, but x cubed minus 3 looks like this. definitely a continuous function, but we're not told about a closed interval, which means an absolute maximum and absolute minimum aren't guaranteed. So I'm not going to do that work. Ah, there we go. Continuous function on a closed interval. And so you should know the relative shape of x cubed minus 3, and that's x cubed with a y-intercept of negative 3, so slid down from the normal x cubed. Oop, not an arrow. And if you know the shape of x cubed minus 3 on the closed interval negative 3 to 5, you already kind of know your answers. The absolute minimum is going to occur over here at negative 3, although I do have to find that y value, and the maximum is going to occur at 5. Although this is calculus and we're playing by a special set of rules, we need to show everything. But knowing where you're going always helps. So first I'm going to need to find critical values. Well, I guess after we think about the shape, continuous function on a closed interval. Maybe I should go back and write that. Y equals x cubed minus 3 is continuous on the closed interval negative 3 to 5. So a maximum and minimum are guaranteed. Oh no, that's an E. Okay, so we'll start taking derivatives. The derivative of x cubed minus 3 is 3x squared. Let y prime equal 0. Y prime is always defined. Zero equals 3x squared, and 0 is equal to x. Okay, so we found all the critical values, just the one of them, x equals 0. That's not where x cubed minus 3 has a maximum, and it's not where x cubed minus 3 has a minimum. Although it does tell me I've drawn this graph wrong. I need to draw so that it appears x cubed minus 3 is perfectly horizontal for just one instant there at x equals 0. Okay, so what do we do next to find global extreme values on the AP test? We evaluate x cubed minus 3 at 0 and at the endpoints. Let's go erase. So let's say using x equals negative 3, y equals negative 3 cubed minus 3, and that's going to be negative 27 minus 3 more is negative 30. I kind of knew that was going to be the lowest place. Let's make sure. So using x is equal to, what should I do next? I'm going to go in order, 0. Y equals 0 cubed minus 3. Y equals negative 3. So I know negative 3 is not a minimum because 30 is smaller. So using x equals 5. Y equals 5 cubed minus 3. 125 minus 3 is 122. Okay. What's the maximum? What's the minimum? The maximum of x cubed is not negative 30. That's minimum. Sorry. Let's try that again. The global minimum of x cubed is negative 30. Can I get a different color, please? Probably not. The absolute minimum of x cubed minus 3 on negative 3 to 5 is negative 30. The absolute maximum, the global maximum of x cubed minus 3 on negative 3 to 5 is 122. The maximum occurs at x equals 5. The minimum occurs at x equals negative 3.